Great. Well, we should kick off again. So our next talk is going to be from Reinhard Höhler, and he's going to tell us about packings of soft sticky particles.
Thank you. Thank you for the invitation to participate in this very nice workshop. To introduce the subject of my talk, some words about sticky particles and their assemblies in general. As a function of length scale, at the smallest length scale, angstroms, you might consider atoms as particles that interact with via stickiness, and depending on the nature of the interactions, you get all these different crystal structures and materials on the macroscopic scale with properties depending on the structure. You can play the same game on the nanoscale, where many groups have been working with patchy nanoparticles functionalized by DNA strands, as we've already heard. And you can do just about any structure, I believe, by coding it via these directions. Here's an example of adhesive chloride structure, and you get little bits of material of it, even though one of the difficulties that still remain to be overcome to make this whole thing even more relevant by applications is the quantity of material that you can make, because the process is very sophisticated. And if you go to still a higher length scales, you end up with the particles I show up here, drops and bubbles. This is a field where I've been working for many years, and I've been wondering whether we could transpose the same idea, change structure via interactions to the field of drops and bubbles. Why are they nice? Well, they are frictionless objects in contrast to granular particles, which is helpful for self-assembly. They are soft. We heard about the slight mismatches that can make large-scale assemblies difficult. So these mismatches can be accommodated. And I will tell you in my talk how pretty different structures can arise if you ramp up a parameter, which is stickiness, which can be tuned by chemistry and in some cases via temperature, as seen in this cluster historic work by Hendrik Prinsen from the 80s. And one of the results will be this spider web structure, where in a foam, all the liquid segregates from the gas and accumulates into these little droplets of concave shape. Okay, so what kind of new equilibrium packing structures can we get, and can we derive from this useful materials, or possibly metamaterials that are interesting? First point is a brief review of what bubbles do and how they assemble in the absence of any attractive interactions. This is foam science as it has been developed over many years, but very much like in the first talk this morning, you can induce long-range order by shear, and you easily get, when you produce using microfluidics to make a very large number of bubbles, a long-range FCC order of that. Now, what kind of control parameter do you have in that case? It's the amount of liquid that you have in the system and that you can suck out or push in. And we talk of dry foams and wet foams, which take on crystalline shapes, which are illustrated here. This is experiments. We see this the structure, which is not so evident to see, but it's actually a BCC structure seen from a 2-2-0 direction. And as you scan through liquid fraction, you've got a structural transition that happens. That goes to the FCC structure, which is seen in the 1-1-1 direction. And if we combine this with surface evolver simulations, we see that this transition goes along with a minimum of energy, where crossover between minimal energies, which corresponds to this FCC-BCC transition. So the bottom line of all this is that we've got a BCC structure, an FCC structure, and if we put even more than 26% liquid into the structure, well, we end up with bubbly liquids where the bubbles freely float around. Here we've got a jamming transition, a crossover from solid-like to liquid-like behavior. Okay, and what can we get if now we introduce by some chemical tricks, co-surfactants, salts, an adhesion? Let me first talk about two bubbles. Two bubbles small enough so that gravity doesn't deform them, maybe floating through a horizontal plate. This is actually a microscopy picture taken in that configuration. If you've got no adhesion at all, it's just the two spheres sitting there and touching tangentially. If you introduce an adhesive energy, then there will be a contact angle. These interfaces will meet at a non-zero angle, which is larger and larger to the extent that you have stronger adhesion. There's the Young-Dupree relation, which is a simple force balance condition, which relates the intensity of the adhesion energy and its angle. Okay, and what happens if you pull on that system? What is the contact law? Well, in granular physics, we know the Hertz law. In the case of adhesion, we know the GKR theory. All this is no longer the right way of looking at things if you've got drops and bubbles, because here all the deformation energy is stored in the interfacial energy. And there's a very nice theory by Morse and Witten, which can be solved analytically. And there's surface evolver simulations that give this kind of scenario where we see the force displacement relation of this kind of thing, depending on the contact angle. The top line here is the nonlinear force relation, force displacement relation if you have for a repulsive system. It's not like the Hooke's law, it's a little bit nonlinear. And if you put in more and more adhesion, you get these curves here, and you can have compression as well as traction up to a snap-off point, which is well defined. There is equations behind all of this, but this is not directly a packing story. Therefore, I skip over this. And if anybody's interested, I'd be happy to talk about it at some other occasion. Okay, so now how do we figure out what kind of structures will be stable in view of these new interactions? Well, this brings in a question that's been asked in the 50s of the 20th century on the level of the atoms. Max Born at that time was writing a book about the theory of crystal lattices, which is still useful in this new context. He figured out a necessary criterion for crystal stability in terms of elastic constants. You only need to consider two elementary modes of deformation. And due to the symmetry of the system, that will be enough to ensure that the system will be stable with respect to any kind of deformation that you apply. And in the language of crystal physics, it's the elastic constant C44, which is essentially about shear, which has to be positive, and some other elastic constant, which is about uniaxial pulling. And if you've got positive restoring forces for the two, well, the thing is stable. Okay, so now we take our FCC packing. This is a surface evolver simulation of that kind of thing. And you ramp up adhesion and you watch what happens to the restoring force in the case of a shear that you apply to this thing. The black curve is the case where you have no adhesion. And you see the elasticity falling to zero at 26% liquid fraction. This is just the random, the closed packing fraction of the sphere assembly. No surprise here. So we've got a stable crystal up to here. And now you make the thing adhesive more and more. And you notice that the FCC structure is no longer stable over here. And there's even strange things happening here, a drop of elasticity. And we're going to figure out what that means in terms of actual structure. So I first thought maybe if the FCC structure no longer is stable, what can it be? Possibly simple cubic structures. That would be very nice because they have metamaterial properties I'm going to come back to. So I try to figure out whether we can have stable, simple cubic foams in the presence of adhesion. And I did the Born check. Well, the C44 of the simple cubic thing is always negative if it's repulsive. Of course, you don't have any restoring force in that case. And to the extent that you make the thing more and more sticky, you've got a big simple cubic phase that extends more and more out in parameter space. The uniaxial mode is always positive, as a positive elastic constant. So indeed, there was a new phase coming up, which doesn't exist in ordinary foams, which have no adhesion. And then there's this other question about the strange drop here. And to understand what's going on here, we have to go back to Mr. Plateau, Joseph Plateau, Belgian physicist from the 19th century, who's been among the pioneers of observing, who's been observing foam structures. He looked at structures like this. This is a dry foam. That's what you typically see in your kitchen sink when all the water has seeped out of the foam. And what you see then is these dark lines, which are actually junctions between the films separating neighboring bubbles. It's in these junctions, which are in honor of this gentleman called Plateau borders. All the liquid accumulates, and he formulated some laws telling us how the geometry of the topology of this assembly must be. 3 films join at Plateau borders by 120 degrees, and these borders themselves join by 4 at vertices at the tetrahedra angle. And now we may also have a closer look at the cross-section of with these Plateau borders, whose curvature is set by the Laplace pressure. So there is a tangent circle that I drew here to highlight the radius of curvature of this interface, and the pressure difference between the gas phase and the liquid phase sets the curvature, which must be everywhere the same in that system. Okay, so now we come back to this strange behavior of the shear modulus when you enhance the adhesion. Here I showed you the cross-section of a Plateau border in the absence of adhesion with a contact angle of 0. What happens if I ramp up the contact angle to 30 degrees? Well, then all the curvature is condensed in these corners, and there's nothing left. No curvature is left for the faces here. They become flat. That means that there is no longer any pressure difference between what's inside and outside the Plateau border. If ever you go a little bit up more with your angle, then you have an opposite curvature, and there is a Laplace pressure which is pushing out the liquid from these Plateau borders. They do a collapse and they sizzle down to a size so small that nanometer range interactions between the surfactant covered interfaces come into play and stop the evolution. So there's something like an implosion of the structure here. And well, digging into the literature, I again came up on this Hendrik Prinsen in foam physics. Very often, if you think you've found something new, you look at literature, and Hendrik Prinsen did something in 1980 something which is already at least a precursor of that thing. So he didn't have microfluidics. He couldn't do these large structures, but he could produce at least 3 little droplets here, which were of almost equal size. And in his system, he was able to tune adhesion via temperature. And we see here where something which is very much similar to the cross-section of a Plateau border, which shrinks and shrinks and collapses in the end. And so this is a kind of simplified example of the thing that I was showing you. Now I come back to surface evolver simulation of exactly the same thing. And here we've got the structure at 0 angle and a structure at 35 beyond this transition. You see that the bubble shape has become very much modified. And in this lower picture here, I made the films transparent so that you can look into the structure. And you see that the Plateau borders have indeed collapsed to wires. Well, in the surface evolver, you don't have these molecular interactions modelized. It just sizzles down to a line, really. And all the liquid is segregated from the gas beyond this transition and forms this regular array of droplets. So it's indeed a very new structure that can be generated by starting from an ordinary FCC foam and just by introducing adhesion. And I played around with different other structures, and I found that the initial phase diagram that I showed you, that was just this line actually, where liquid fraction is here, the control parameter, where you have the VCC phase, which is not shown here, it's over here, the FCC phase, and then bubbly liquids, becomes a complex phase diagram with lots of new phases, and in particular also this Plateau border instability that comes up here, and which generates that kind of shape. Of course, I was not able to find all the possible minimal surfaces, minimal in the sense that you have a minimal energy, which is a combination of interfacial energy and the places where two bubbles meet, where adhesion comes into play. And a second contribution of interfaces where there is gas facing liquid. So that's a more general minimization problem than the one that Kelvin considered or that Ware and Phelan considered. So there is here a parameter space where possibly a lot of other structures exist that we do not know of yet. Now, why is this interesting in the sense of applications? I come back to plateau borders that I already showed you. And let's imagine what happens if I take one of these plateau borders, which are the building blocks of any kind of dry foam. I solidify this, which is very often done in industry, which is easy to do. And now I pull on this thing. How will the thing react? Well, the first reaction will be a bending. You can just bend these sticks and elongate it in response to this force and to relax this force. This is why foams are so soft. Because, well, you know, foams of various kinds, and everybody knows that if you push on the foam, it's soft. It's not just because there is not so much matter in there. It's due to this particular geometrical organization, which makes that the elastic elements, which are like sticks, are working not in traction compression, but in bending mode. If you take a plastic ruler, you bend it, it's very easy. You try to elongate it by pulling with the same kind of force, it's very difficult. So it would be a very different kind of material if you align these little sticks so that if you pull on the thing, you have traction and not bending at the level of the elementary plateau borders. And there is a very large activity in the community of mechanical metamaterials aiming to produce structures which have this stretch-dominated property. The simple cubic structure is the simplest of stretch-dominated assemblies that you can think of. It has the inconvenience of being very anisotropic because it's only in the directions of symmetry that you have this stretch-dominated property. But still, it is the starting point of something which is an interesting mechanical metamaterial, and therefore finding foams which are the precursors of that kind of material and which are intrinsically stable, which can self-assemble, is a nice thing. And you also have these strange spiderweb-like structures. I think they could have interesting acoustic property. You could think of them as 3D Bragg lattices, which have a symmetry, a regular spacing of these elements. You could very easily deform them, tune the properties of this Bragg lattice, maybe use this for beam steering. So there's a lot of imagination can develop in view of these things. Of course, it would be very nice to have even better metamaterials. People are playing with that kind of structure, which is produced by microlithography. It is assemblies of sticks and not plateau borders. It is actually little sticks. And in view of the stacking of these pyramids here, you have a stretch-dominated response in any direction. Would be great to produce a foam that self-assembles and which takes on that kind of geometry. So I don't know whether it's possible, but it's a nice dream I'm trying to investigate. And let me finally say a few words about experiments, because of course it's very nice to have pictures and simulations, but having the material sitting on the table is yet another step, which is difficult to achieve. Maybe I'm not going to go too much into the details. I don't know how much time I have. Okay, so anybody interested in experiments is invited to talk to me, and I can tell you about surfactant chemistry and how you tune the constitution of the films to an adhesion. I can tell you about inverted fluidized beds where you stabilize liquid fraction and so on. And I can tell you about experiment results that we have, which are not quite yet this spiderweb structure, but something very close to it. And I just skip to the conclusion, which is that adhesive bubble interactions can indeed induce new order foam structures. And one can easily think of useful properties that could be developed by solidifying that kind of thing. There are many challenges, many open issues, such as can we identify minimal energy structures, stable foam structures, which would have this stretch-dominated mechanical properties in any direction. And another big issue is structural athermal transitions. In the case of colloids, you have thermal agitation, helping you to explore all possible configuration. In this case here, you must use assisted self-assembly by, for instance, shearing and deformation. This is yet another topic. Anybody interested in that, I would be happy to sit together with you and talk about it. Let me finally thank Reinhard Höhler, Dennis Ware, Stefan Grützler, Philippe Poulain, Andy Krainig, and my PhD student Jordan Sidnaki, without whom all this would not have been possible. Thank you for your attention.
With the Born criterion for that, does that imply stability against a sort of a loss of homogeneity, flocculation?
Yes. So is it a necessary condition? It's not a sufficient condition. I agree.
If you showed a phase diagram of contact angle against lithographs, I didn't understand why the horizontal axis is not filled in, at least up to 36.
So at least after 36.
You know, this transition from FCC to BCC, and why is there a gap?
In this region here, if you look at the shear modulus of FCC, but it is negative or zero. So beyond 26% liquid fraction, the bubbles just touch each other anymore. And so the whole thing is not a solid. And here, of course, you could say maybe if there is adhesions holding the bubbles together, this could still be an FCC ordered face-centered cubic thing, but it has a negative shear modulus, so it will not remain stable even if you only take the Born criterion, which is necessary but not sufficient. If you go further on, there's a kind of re-entrant BCC transition, strange thing, because BCC is usually over there. And probably you could have here FDC with defects in it. But then there's maybe foam structures nobody ever thought about that could exist here, and it would be great to find out what kind of new structures can exist.
How could you find them?
Good question. So maybe this workshop is the occasion to do some brainstorming. Of course, you could also do it the other way around. You could say, I would really be happy to use that as a starting point for material. So if I stick this into the surface evolver and I put in a lot of adhesion, is the thing stable? Possibly it is. Maybe the number of possible structures is infinite. Could be. So it's a nice thing to start with those you find interesting for some reason and to see how you can stabilize them. Yes.
Any other questions?
Is there an experimental upper limit to how large the contact angle can be? I mean, obviously 90 degrees, I think.
The answer is different for foams and for emulsions. This is something to do with the Young-Degree equation that I showed you over here, where for a given adhesion energy, the angle will depend very much on surface tension. For emulsions, liquid-liquid interfaces, you have interfacial tension, which are 2, 3, 4, 5 millinewton per meters. For foams, you're an order of magnitude beyond, and this makes life more difficult for foams. The best we could do so far with foams is something like 25 degrees, which is just below what it takes to do the spiderweb transition. The trick here is to introduce ions in the solution and to produce an electrostatic attraction effect mediated by these ions between equally charged surfactant layers. And it's not just the charge, but also the size of the ions which matters. So there is some tricky surface chemistry, and we're fighting to get this thing higher up. In the case of emulsions, you can have very high angles. I don't think there's any limit really here.
Okay, thank our speaker again.